here at Rutgers, and so this was. Emily will explain some of the background, but it's a problem that sort of has been bothering me for forever. I see Alejandro is here. Alejandro tried to take a crack at it, but it sort of didn't. Yeah, it didn't. So you remember this well, Alejandro?
Oh yes, too well.
Yeah.
Yes, I'm glad that someone was able to tackle it. Yeah, it
Yeah.
was my first little project with you. Yeah.
Right. Right. Okay.
Great, thank you for having me, and thanks for the introduction. This is joint work with Yusra and with Siddhartha too. And so we're going to talk about positivity of interpolation polynomials. And so I must needs start with, what is an interpolation polynomial? Well, this is a family of inhomogeneous symmetric polynomials. And we have two sets of parameters. We have the n parameters up in the exponent there. That's called rho. We're usually going to have rho be a staircase shape, so n minus 1, n minus 2, and so on. And then we also have this index in the bottom, which is a partition. And this is going to end up being a basis for the ring of symmetric functions, hence we have one per. Is there a question? So this is indexed by partitions. And the total degree is the size of the partition. And they vanish at these points corresponding to smaller partitions. So any smaller partition or a partition of the same size that's different than the index is going to correspond to a vanishing point. And so this has a very simple, sort of very attractive, simple description, but we'll see it actually connects to a lot of wonderful things. And these properties, the vanishing and the degree and all that, characterize our polynomials up to a scalar multiple. They were originally introduced by Siddhartha in 1994, and they're motivated by earlier work with constant on the, excuse me, on the generalizations of the Capelli identity. So they have some really interesting connections to Jordan algebras and stuff like that. So the connection I want to focus on, though, is with Jack polynomials. When we look at that staircase shape, rho is the staircase, n minus 1, n minus 2, and so on, times a parameter r. Then we have some extra connections, and this special case was studied with Sahi and Knopp back in the day. And their main result was that the top coefficient, if you just look at all the top degree terms, you get the Jack polynomial with parameter 1 over r. And we're going to use alpha and 1 over r kind of interchangeably throughout the talk. And so because of this top component being the Jack polynomial, these are sometimes called interpolation Jack polynomials or shifted Jack polynomials or Knopp-Sahi polynomials. And so now the question is, what's a Jack polynomial? If you're not already friends with Jack polynomials, what are those? So these are a basis for the ring of symmetric functions. That
if you don't know Jack, so to speak, right?
You don't know Jack. So these are an important basis for the ring of symmetric functions, and they play a prominent role in McDonald's book. And they're eigenfunctions of some certain differential operators. That's one way to define them. They also have this cool combinatorial connection. So McDonald introduced this normalization and said, let's look at the coefficients when we expand in terms of the monomial symmetric functions. And he conjectured that those coefficients should be positive integral polynomials in our parameter alpha. So Knopp and Sahi proved this by getting a really nice, beautiful combinatorial formula in terms of admissible tableau. So you take tableau satisfying some certain admissibility condition and you have a weighted enumeration of them that equals the Jack polynomials. And you can see already here we have our first positivity result, that the Jack polynomials expanded in the monomial basis here have these positive integral coefficients, and we're going to be looking at further and further generalizations and eventually proving them. So this conjecture of Knopp and Sahi that we're going to prove says, let's generalize this positivity result to the setting of the interpolation polynomials. So just like with the Jack polynomials, McDonald had to make a normalization, we're going to normalize the interpolation polynomials. And there's some coefficient out front. Don't worry about that. Look at this, x goes to minus x. That's going to
Emily, it's the same coefficient as in McDonald.
Well, this -1 wasn't there.
Yeah, right. That the minus one.
Yeah, this actually has a nice combinatorial description in terms of hooks, but who cares? We're not going to get into that in this 50 minutes. But this minus sign here is going to affect our vanishing. So now instead of having vanishing at partitions plus a shift, it's going to be minus the partition plus a shift. And when we expand in terms of the monomial basis, we get these coefficients up to some power of alpha. We get these coefficients here. And the theorem, originally conjecture, now theorem, is that these are positive integral polynomials in alpha. And this is the most specific kind of statement that we're then going to generalize and refine and eventually prove. So the first step in moving toward a proof of this is to go to the non-symmetric world. Oh, I forgot I had an example planned. Sorry, I love examples, so I added a bunch of examples in at the last minute. So what's an example of one of these symmetric Jack interpolation polynomials? I claim this is the guy indexed by the partition 2, 0. And if you first just look at it, it's a jumble of symbols. But the conditions, right, were that it should vanish at these points. It should vanish at the smaller partition shapes, 0, 0, and 1, 0. And then it should also vanish at the other partitions of size 2. Well, it's a small case, so there's only one, namely 1, 1. And for the first 2 points, when we set x2 equals 0, lots of the stuff here disappear. The way that I wrote it, this whole chunk disappears because there's an x2, this whole chunk disappears, this disappears. And so we're just left with this product, these two x1 factors, which are exactly what they need to be to cancel out for these 2 points. So it has this really nice vanishing, almost like term by term. But when we look at this last point here, when we set x1, x2 so that it corresponds to the shape 1, 1, then the vanishing is more complicated. These terms, the way I've written it, they have to combine together in sort of a miracle way to make 0. And so there's going to be kind of a recurring theme about how these vanishing conditions come up in smaller and smaller chunks of these polynomials. So the non-symmetric case, our first generalization. Knopp and Sahi, when they proved this admissible tableau formula for the homogeneous Jack polynomials, they actually did it in this greater generality of non-symmetric Jack polynomials. And these are called the non-symmetric Jack polynomials. We're going to denote with E, and now they're indexed by compositions because they're going to be a basis for not the ring of symmetric polynomials, but all polynomials. And these again can be defined as eigenfunctions of certain operators. Now they're the trigonometric Dunkel operators that were introduced by Cherednik, and Heckman and Opton were the first people to consider this non-symmetric Jack polynomials. And up to this appropriate normalization, we have again a positivity, or Knopp and Sahi have again a positivity result. If you expand in terms of ordinary monomials, now not symmetric monomials, ordinary monomials, you get again positive polynomials in alpha. Everything there translates over into the interpolation story. We have an interpolation analog in the non-symmetric world, which we're still going to denote by E, so it's easy to remember what goes with what. And this has the degree of the size of its index, the size of this composition eta, and it has a vanishing condition for each smaller composition, gamma, and all the compositions of the same size except itself. But now we have to be a little bit more careful how we define the vanishing point. We're not just going to take gamma as a vector and add r times the staircase to it. We have to sort of sort gamma, add the staircase, and unsort it. Or you can think of it as multiplying our staircase row by an appropriate permutation and adding that. Okay, so just kind of taking into account this the fact that these guys are not sorted in the way that we do the shift. But we still have one vanishing point for each one of these sets of compositions, each one of these compositions. And this again characterizes the polynomials up to a multiple, the fact that it has this specific degree and that it has these vanishing conditions. So in our special case here, we have that the top degree term is again the non-symmetric Jack polynomial. So everything is analogous to what happened in the symmetric world, which is always a good sign that you have the right non-symmetric generalization. And you can find out a lot more about these. They're really neat interpolation polynomials in these papers in my reference at the end from Knopp and Sahi separately. And what about the positivity thing? I promised you positivity results. So the non-symmetric generalization of our main theorem now has to do with, you guessed, a normalization of this guy. We have the same analogous coefficient out front, and we again send x to minus x, and we get this polynomial, which we're calling f here, f r delta eta. And now when we expand in the ordinary monomial coefficients and we adjust the appropriate multiple of alpha, then we get positive polynomial coefficients yet again. So I'm a combinatorist by training. So whenever I see that something is positive, it's my goal in life to have a combinatorial interpretation of it. And I'm so happy that we end up getting one, but we still have a bit more story before we can get down to the combinatorics. So we have these now non-symmetric generalization, and we're going to end up breaking this further down. We're going to prove a stronger result. So we've gone symmetric, non-symmetric, and now we're going to refine it.
Now we should point out that non-symmetric implies symmetric.
Yes, non-symmetric implies symmetric. So I'll do an example at the end, and hopefully that'll make it clear how you can build all the pieces back up, right? I'm breaking it down now, symmetric, non-symmetric, and then we're going to refine it. And at the end, there'll be an example which sort of shows how you go all the way back up to the top. So just for some examples here, if I give you the non-symmetric interpolation polynomial indexed by 2, 0, it looks like this. And you might notice some similarity with the symmetric guy. So this big chunk here in large parentheses, we had that exact expression occurring before, but with a different coefficient. The same thing down here. We had an x1, x2 times something, and we had an x2 plus 1 plus r times an x2. None of this is an accident. This is going to come up in our refinement. And so now when we look at our vanishing conditions, we have a lot more of them, because now there's not one per partition, there's one per composition. So we have these 3 same vanishing conditions as before and 2 new ones with compositions that are out of order. And the same nice arguments go through for why this vanishes. At the lower points, it vanishes in a very pretty way, that there's these 3 chunks and each chunk individually vanishes. And then when you're at the equal degree, it's a little more complicated how the pieces combine. Similarly, if we look at the other 2 non-symmetric interpolation polynomials of size 2, we get these nice simple expansions. Again, we have that x1 times x2, and we have the same x2 plus 1 plus r times x2, the same factors coming up again and again and just being combined with different weights out front. That's what we're going to, that phenomenon is what we're going to explain. So our tool here is what we call the dehomogenization operator. And we're taking advantage of the fact that both the homogeneous Jack polynomials, this f with an alpha up top, and the inhomogeneous interpolation polynomials, f with an r delta, are both bases for the polynomial algebra that we're interested in, for polynomials in alpha and r and x1 through xn. So we can define an operator, a linear operator, that maps the homogeneous guy, the homogeneous Jack polynomial, to the corresponding non-homogeneous interpolation Jack polynomial. Hence the name dehomogenization. We're dehomogenizing the Jack polynomials. And since that's a basis, we can apply this operator to anything. And this operator has nice properties, like it preserves the space of symmetric polynomials. So it's going to map the symmetric versions to the symmetric versions, and even without the constants out front, when we look back at the original symmetric guys, the p's, that'll also map them to the corresponding homogeneous guy. So it's really dehomogenizing in a good, strong, nice sense. And this is a non-symmetric analog of an operator that Knopp and Sahi already defined before. And this is going to be how we refine our result and get down to smaller pieces that then we can explain combinatorially. So we consider this application of our operator not to the entire Jack polynomial, but sort of term by term to an individual monomial. The Knopp-Sahi combinatorial expansion for the Jack polynomials said how to expand them into regular monomials. And so we're going to think what happens when we apply just to a regular monomial. We call this a bar monomial, and we denote it almost the same way you denote a regular monomial, but with this little bar underneath the composition. And this is partly motivated by this special case when there's only one variable, we get a rising factorial. Well, if it weren't for this switch of x to minus x, it would have been a falling factorial, which makes the notation even more appealing. But also we already had this bar on top for our vanishing points, so that notation was taken. So this is sort of a part of our general part of our motivation for this notation. And in general, we're going to have an expansion like this. Our bar monomial equals the monomial that we dehomogenized plus lower stuff, lower degree terms. And our theorem is going to be that all these coefficients that appear in front of the lower degree terms are polynomials in our parameter R. And we have a bound on the degree that's going to allow us to go back up and and get the results we originally wanted in the Jack setting. And this will imply that positivity, because now we'll take the Knopp-Sahi result, which says how you combine monomials, regular monomials, in a positive way to get Jack polynomials. And then we'll apply our dehomogenization operator and get a positive combination of bar monomials, which equals our interpolation polynomial. So all the positivity is going to go through because of that. And one way to understand the dehomogenization operator is that if you take any homogeneous polynomial and you apply this operator to it, you're going to get that top component is what you started with. And you're also going to get the lower vanishing conditions. It's not hard to prove this theorem, because when you expand f in terms of the Jacks and map it over, you get an expansion in terms of the interpolation polynomials, which all have these lower vanishings. And one nice property of 0 is that any linear combination of zeros is 0. So all these vanishing properties go right through. And now at least we have a characterization of our bar monomials that lets us recognize a bar monomial. So if I tell you that this is a bar monomial, sorry, was there a question? If I tell you that this is a bar monomial, I can check that. I can say, well, look, it has the right top component, which is x1 squared.
Lisa, perhaps you can you do a global mute or something, and then Emily could unmute, or?
Yeah.
I'm not sure if I'm a host. I think Ishi has to do it.
It's okay. Right, so I claim to you that this is one of my bar monomials, and I can check it. I can check that the top component is what you want, and I can check that it vanishes where you want. And you may recognize this as one of those chunks that kept occurring in my earlier example, right? This was that big chunk that had parentheses around it. And if I look at the other guys of degree 2, we'll see the other chunks. Oh, x1 times x2, that kept occurring in the examples. x2 plus 1 plus r times x2, that kept occurring in the examples. So what we were really seeing when I wrote those interpolation polynomials down was that I had already decomposed it into bar monomials without telling you. And then all the vanishing properties were exhibited in a really nice way, especially for the lower vanishing more than the upper vanishing. So how do I construct these things? Right now you kind of can see, peek behind the veil, how I'm constructing my interpolation polynomials. I'm using the Knopf-Sahi tableau, and I'm using the bar monomials. But where am I getting the bar monomials from? How am I getting these pretty expansions for them? And why are they positive at all, even once I construct them? That's the level we've gotten to down now, which is wonderful because it's time then to talk about the combinatorics. That makes me happy. So how do we get a handle on these things? How do we construct them? Well, if you have regular monomials, just plain homogeneous monomials, you can build them up with operators. And I'm going to build them up in a way that you might find a little bit strange. So if I want to increase the degree of my monomial, instead of just multiplying by an x, I'm going to apply this strange phi operator, which rotates my variables and then multiplies by one of the x's. It raises the degree, weird, however it might be. And then once I have the sequence of guys that I want, I can permute them. So I use these adjacent transpositions, the SIs, to switch around the x's until I get the sequence of exponents that I want in the order that I want them. So I can do this. I can build up all monomials using this weird twist and multiply and then permuting things around.
Maybe, Emily, maybe I could just say a word, because many people know that this is really an affine reflection.
Yes, yes.
So it's for the, I mean, there is an affine root system, and this is a reflection.
Right, and we didn't make up this weird phi operator.
Yeah.
But this is also the one that generalizes nicely. So when we try to go to bar monomials, we get analogous recursions. So there's this phi1 operator, which does almost the same thing, except there's this non-homogeneous aspect to it. So when I twist around the variables, I also add one here. And that's going to create lower degree terms. It's not going to affect my top degree, but it's going to affect the lower degrees. And similarly, instead of just this transposition SI, I'm also going to have this other term. And this division here by xi minus xi plus 1 means that's also going to mess with my lower degree terms. It's not going to mess with my top degree term. So this is a non-homogeneous analog. And it's the correct one. These operators act on my bar monomials just the way that their homogeneous versions acted on regular monomials. And this gives me a way, at least with my computer, to construct the bar monomials. I don't have to go fishing around doing linear combinations of things to try to make vanishing. I can just iteratively build them up with these operators. And it also gives us a method of attack for proving things, because I could try to pass properties of the bar monomials through these operators. And that works well for the vanishing properties. But unfortunately, it doesn't work well for positivity. So this sigma operator with its minus signs and its divisions, it doesn't preserve positivity in a nice way. So we can't just use this to go ahead and get a positivity result. What we had to do was actually solve our recursion, find an explicit combinatorial formula, and then prove that our combinatorial formula behaved nicely with respect to these operators. And that allows us to build them up. Okay. So what's our combinatorial object? How are we creating these guys combinatorially? We're going to play a solitaire, a one-person game on the diagram of the indexing composition. And every time I make a move in this game, it's going to shrink my composition by 1. So a valid move takes whatever composition I'm at the moment, and then I do 2 steps to it. The first step is that I look at all of the rightmost boxes. So I'm thinking of this diagram, Farrer's diagram, as each part of the composition is a row that's sticking out. And I look at those guys that stick out the most and pick the highest one. That's a special box. We call it the critical box. And I'm always going to delete it. Then I look in the same row where I deleted that box, and I can take some of the other boxes and shift them around. shift them from the end of that row into another row. I have to do this in a way that either moves them up and to the left, strictly to the left, or down and weakly to the left. So I can move it left or I can move it straight down and make a new composition shape. So this is easier to see with examples. So I just keep doing this until I run out of boxes. And a game then looks like this. I start out with a shape, let's say 183025, and I draw this picture of it. And now I look for the rightmost box. That's the one here in the row of size 8. It's the unique guy. I'm going to have to delete it. And then these other 7 boxes here, I can choose to move some of them into another row. So say I choose to move these 5 boxes from row 2 up and to the left into row 1. Then I wind up with this shape. Now that critical box, that rightmost box, is in row 1. So I'm going to delete it. And then I could move some of these other boxes in row 1 somewhere else, but it's optional. I can move as many of them as I want to, including none. So that's what I'll do right now. I'm just going to delete this box and not move anything. Now I have a tie. I have 2 equally sticking out boxes. I pick the higher one. I have to pick the higher one. And then I move 2 other boxes. It's my prerogative to do that. I move them into row 2. So it's okay to move vertically when I go down, but not when I go up. And I keep on playing this game. Now the last row is the one where the critical box lives, and I choose to move this 1 box 2 rows away. It's okay to jump over other rows. Now, when I do this move, you can see it's even okay to jump over higher boxes. That's fine. There's no conditions on that. And I keep on doing this until I get a really boring shape. Here, all the rows are either of length 2 or 3. And this is going to prevent anything else interesting from happening. When I look at that highest box here, there's nothing else I can do but delete it. None of these other boxes in its row can be moved without violating these rules. And so I'm just one by one going to delete these boxes. This box, again, there's nothing else I can do in this row except delete the box. Can't make any other moves, etc., etc. I'm going to just do that until I run out of boxes. And that's an entire game from start to finish on this shape. So we do this, we keep iterating, and we get a set of possible games on each shape. We're going to need to do some kind of weighted enumeration of them. So how do we weight them? Well, I weight each move individually, and I'm going to take the product of those move weights. So if I move any boxes, once I delete a box, if I take any other boxes from that row and slide them elsewhere, then the weight of the whole move is just R. If I just delete that critical box and I don't do anything else, I'm going to get a linear weight here. I'm going to get X indexed by that row where I deleted the box. So if I deleted the box from row 3, this would be X3. And then I have a constant, which is sort of a co-arm, and R times another constant, which actually turns out to be a leg because it doesn't quite look like a leg, but this is one of the longest rows. And so that ends up making this equal to that typical definition of a leg for a composition shape. Doesn't really matter for the purposes of this talk, but it's sort of nice that these constants are like a hook thing. For us, just think of it as there's some linear factor, and the X in that linear factor has the same index as the box that I deleted. And now I just take the product of these move weights. So for that game that we played, this first move included sliding around some boxes, so I just get an R. Then I had this sort of trivial move where I just deleted the box, and that gives me a linear factor. I deleted it from row 1, so there's an X1. Then I had 3 more moves that all get weight R because there's some sliding of boxes. And now for this last bit, these 2 boxes that are sticking out the most, they're in row 3 and row 6. So I get an X2 and an X6. And then I have 1 through 6. That's these X1 through X6s. And another 1 through 6. That's these X1 through X6s. And so this product that we get is nice and positive, and we can see that the degree is less than or equal to the degree of the shape that I started with, because at worst, I'm getting one linear factor per box. So theorem, if you sum over all these guys, you get our bar monomial. And the proof of this, which unfortunately I'm going to have to kind of sweep under the rug for the sake of time, is that these act nicely with our operators, right? So if you think combinatorially about what's happening to the shape, what's happening to eta when I apply the composition version of these operators, like I'm twisting the rows around and adding a box, or I'm just switching to adjacent rows, you'll see that it doesn't really affect the set of moves that I can do very much. The nature of the moves that are allowed is that they go very well with these operations. If I switch to adjacent rows, that doesn't very much affect where I'm allowed to move boxes to and from, things like those. So we can combinatorially prove that these operators do what we want, because mostly nothing changes, and those few moves that get messed up end up canceling out. And that, when you work through that, you see why these are the correct weights, why this xi plus the coarm plus r times the leg is the correct weight for that trivial move, so that these operators act the way that they should act. All right, so how would we do a full computation of a bar monomial? Well, I would need to show you all the games on a particular shape. And just for brevity, for being able to write this on my slides effectively, when I delete a box without doing anything else, I'm going to put the X and keep working in the same figure as I did on the earlier slides. And now we look at a specific shape, fix this shape 104. And I claim that these are all the games that you can play on 104. This top guy says, delete the boxes in the order that you have to, and don't do anything else. This next guy, I do a deletion. Then I do a deletion with a slide, what we call a glissade from mountain climbing terminology. And I get this shape 111. And now I just delete all the boxes in the order that I have to delete them. And there are 6 games here. It doesn't matter in particular what they are, but I promise you they're a full set. And each one of them is going to give me this corresponding weight. This first guy, which is all trivial moves, has 5 linear factors. So that's the only one that's going to give me anything of degree 5. And what's its top degree term? Well, it's exactly the monomial it should be, because 4 times I delete a box from row 3, that's going to give me 4 x3s. And 1 time I delete a box from row 1, that's going to give me an x1. All the other guys have some r factors which bring the degree down. So it's easy to see from looking at it that it satisfies one of the 2 conditions for being a bar monomial, namely the top degree term is what it should be. It's not easy to see the other property. It's not easy to see the vanishing. So if you were to try and check the vanishing properties here, they wouldn't go through game by game. So when I plug in smaller composition shapes, you wouldn't get that the weight of each individual game vanishes. They would be combining together. But the entire bar monomial would vanish. So we go to Jack polynomials. We have a vanishing condition at the Jack level. That passes down to a vanishing condition at the bar monomial level, but it doesn't go all the way down to the level of games. So that's sort of an open combinatorial problem, is to understand why these non-vanishing game weights combine together to make something that has a vanishing condition for the whole bar monomial. Open problem. So that's how we make the bar monomials. And as promised, now I'm going to show how you would combine the bar monomials together to make a Jack polynomial. And I'll do this for a non-symmetric Jack polynomial. So our
interpolation polynomial.
I'm sorry, Jack interpolation Jack polynomial. Thank you. So again, as I mentioned before, just verbally, we have this admissible tableau expansion here for the homogeneous Jack polynomials, non-symmetric homogeneous Jack polynomials, F alpha. And when I apply the dehomogenization operator to this expression, it tells me how to write the interpolation Jack polynomial in terms of the bar monomials. We get this positive sum over the exact same set of admissible tableau with the exact same weights, but now they're just being multiplied by bar monomials instead of regular monomials. So if I look at this two-step expansion, first from interpolation to bar monomial, then from bar monomial to games, I end up with an overall expansion in terms of two sets of combinatorial objects, in terms of pairs of tableau and games that are compatible in some sense. So here, if I was trying to expand the non-symmetric interpolation Jack polynomial indexed by 201, I would look at all the admissible tableau of shape 201. I didn't tell you the admissibility conditions, so you'll just have to trust me that it's these 6 tableau. And for each one of them, I look at the number of times each letter, each index occurs. So we have here 2 1s, no 2s, and a 3. So the multiplicities in this shape are 2, 0, 1. Same for all the other guys. This has 1 of each, so I get 1, 1, 1, and so on. These multiplicities are going to be the index of my bar monomials. I have a bar monomial of shape 201. I have a bar monomial of shape 111, etc. And these come with some kind of positive weights that are attached to each tableau. Now, when I want to say what's this bar monomial, I have to break it down in terms of games. There are 2 games of this shape. It happens to correspond to these 2 pictures. And then there's 1 game of each of the other shapes. So I wind up expanding this interpolation Jack polynomial down to a combinatorial sum over these 7 games. And the weights that come out in front of them are going to be a weight of the corresponding tableau and the product of the weights of the moves in my game. And you can do the same exact thing for the symmetric guys. This same expression I had up here for the non-symmetric guys with very slightly different notation because we have slightly different tableau combinatorics. That would also pass through the dehomogenization operator and give us a way to expand the symmetric Jack interpolation polynomials in terms of our non-symmetric, non-homogeneous bar monomials with all of this layers of combinatorics. So I think it ends up really pretty at the end, but you have to kind of keep on plugging up all these generalizations and refinements to get down to this bar monomial nugget, which has this nice combinatorial expression for it. So that was the end of what I prepared. Thank you guys. If anyone has questions.
So is there any sort of indication of vanishing from your, I know you said no, but is there any hint that there's some relationship with the vanishing conditions from the algorithm?
So the bar monomials themselves, it's not hard to see kind of analytically or something why they vanish, because if you look back at, actually I prepared these slides here without the animation so I can flip through them better. If you look at the operators that we were using to build up, if you look at these operators, you can see that the vanishing conditions pass through these operators. It's not that bad to think about why. And that's a proof that the bar monomials do vanish. But at the level of the combinatorics, game by game, it doesn't go through very well. So when we look at the weights of our moves here, well, this R isn't going to affect the vanishing conditions, except that the degree goes down. So we sort of have fewer linear factors here that could vanish. when we plug things in. So that sort of hurts us. And then even these x's themselves, when they do occur, the index of the x here and these co-arm and co-leg and everything don't relate back to the original shape. They relate to the shape that we're in right now. So when I get this this x3 plus 2 plus 2r, that has to do with the fact that at the moment, my shape has a bar that goes out 3 places here in this third component, but it didn't have to have that to start with, right? Or like this in the first row, when I get this x1 plus 1, that comes from the first row having length 2. When you look back at the beginning, the first row didn't have length 2, it had length 1. And so it's very hard to say anything about the combinatorial, co-arms and legs you're going to get at some stage after doing a bunch of moves. And even when you can say something, even when you can force a box to be where you want it to be at some point, it might end up just giving you a weight of R, because maybe when you move it, when you delete it, you move some other boxes around and you don't get a factor there. So I would love to be able to say something like that, but unfortunately it's just not an easy problem. So I encourage you to think about it.
It's an open problem, Alejandro.
Yes.
Oh, we'll see.
Yeah. And there's lots of other interesting generalizations that we want to kind of think about in the future, like how you would take this into the McDonald world, or other connections like that. So this is just sort of where we are at the moment, but there's lots of other cool directions to explore.
So a quick question. So currently your combinatorial formula, as you pointed out, it uses sort of 2 expansions, right? First in tableaus and then with this bar monomial expansion. Have you
Yes.
thought about maybe trying to get a direct monomial expansion now that you have this formula that might show you positivity without using the homogeneous result?
So I suppose you could try to do that. We haven't really too much, because I think that the bar monomials are sort of, interesting in their own right too. And so we don't want to obscure them too much. But if I think about like how that would kind of have to go, maybe you could do that by playing a game on the tableau themselves. Like you start with an admissible tableau, and then instead of sliding boxes around, maybe you would be changing weights of boxes or something like that. But you would have to do it in a pretty careful way, because these conditions, like when I slide boxes around, that it preserves a composition shape. That would mean that up here you would have to impose some ordering on the entries and say, okay, I can only change the labels of these entries in a specific way. And also I think that the arm and the co-arm and the leg things that come into the factors wouldn't have as pretty of an explanation in that world.
Okay, thanks. That makes sense.
Thanks for asking. So I was here worried that I was going to run out of time, but I always talk fast. And so something I didn't put on the slides at all was how did we think of this combinatorial formula? Like, where did it come from? And actually, what we were trying to do was understand how do you do sort of a Pierre rule? How do you multiply a bar monomial? We already had come up with these bar monomials, and we had our operators recurring on them. How do you multiply by like a single x? And if you look at the all possible moves you can make from a single game, right? So if I fix my starting composition, and instead of looking at all games, I just look at all one move steps I can make, you get a nice recurrence for the bar monomials. This a bar monomial of size n is really a sum of bar monomials of size n minus 1. Most of them having a factor of r out front, and a single guy having a linear weight out front. So that's where this a single x times a bar monomial comes into play. And then we realize that in this special case, you can kind of rearrange things and get this nice combinatorial looking formula, and bar monomials came out of that.
Yeah, the games came out of that, right?
Yes.
Yeah, so one thing I think that for the usual seminar, if we write on the board, it will take a longer.
It would take a lot longer. Yeah, I think
Yeah,
I didn't
yeah.
adjust for Zoom.
In addition, certainly I think in meetings, sometimes we use the slides, but in seminar talks, mostly we actually, at least a part of this, we write on the board. And then you see, it will take more time.